Good day. For those of you who do not know us, we're the instructional staff for EC 150, professors here in Patel and Bernardino, and Douglas Harder. In this topic, we're going to describe C-style strings. So in this lesson, we will describe what a string is and how that is actually different from a character array. We will then see how we can store a string in a character array. And we will look specifically at what decision was made to store strings in the original C language. We're going to look at this because C++ still uses C-style strings in some circumstances. We're going to look at some of the limitations for the choice of this representation for C-style strings, and that will make us investigate some interesting problems that may arise if you use this format incorrectly. We're going to look at two functions as well that work with C-style strings. Specifically, we're going to calculate the length of a string and compare two strings to see whether or not they are the same. Now, a string is by definition a sequence of characters meant to represent some sort of expression in a particular language. Consequently, all the characters or all the entries of a string must come from a fixed and known alphabet. Well, if we are doing this, then it makes sense that we could actually store such a string in an array. Now, if the phrase is in English, we can use a character array in C or C++ because ASCII can encode the English language. And that's about it. Almost every other language has at least one or two extra characters, if not an entirely different alphabet. If you want to create a string from a different language, you must use Unicode characters, and consequently you would have an array of Unicode characters. Now, for English, if we are using ASCII, there are a few extra characters such as a new line and a tab character, and these can be used for basic formatting. If you wanted to do any more or detailed formatting, you'd use some sort of markup language from XML, such as, for example, XHTML. Now, the other thing with strings is up until now, we've only used literal strings. And literal strings cannot be changed. But if we are storing a string in a program, we may actually want to start making changes to that string, or edits, such as adding additional characters, deleting characters, or replacing a character with another. More later on, you may want to do things such as searching for a substring, or finding a common substring between two different strings, or finding the length of a string, or performing some sort of other edit globally. Now, what strategy could you use in C++ to store a string? The first point that we're going to see is that the obvious thing is to use a character array. So here, phrase is declared to be a character array of capacity 100. And in this case, we see that the first 8 entries of that array are initialized with the phrase good day. Now, all other characters after the Y will be initialized to the default value of a character, and that is the null character. Now, one question you must ask yourself is, how do we determine where the end of a string is? So, for example, we may want to print this string to the screen. We do not want to print all 100 characters. We only want to print the string which ends in the character Y. So the question is, how do we record and indicate to the programmer how long the actual string is? That is, how do we denote which strings are part, or which characters are part of the string, and which ones are just part of the capacity of the array? One solution is to have a second local variable. So here the character array has capacity 100, but only the first 8 characters are part of the string. And so I could include a local variable. The length of a string will never be negative, so I will declare it to be unsigned int. And this phrase length variable will store the number of characters. If I change the length of the string, say add more text to the end of it or delete the word day, then I would also have to change the length of the string, or I'd have to update the variable phrase length. Now, in a sense, this is a problem because at this point you must now pass around 2 variables. First, the array itself, and then the variable that is storing the length. Now, suppose you were writing a message to a friend on a piece of tape. You're not allowed to mutilate the tape, and you'd like to pass that message on. You can definitely indicate to your friend where your message starts. But the question is, does it end with a period? That is it only one sentence? Or does the message continue after this, maybe perhaps with a number of blank spaces? Well, if you were passing this on to your friend, a reasonable solution would be to use something that is not part of the alphabet to flag the end of the message. So you might just add a scrawl, and that way your friend knows that that is the end of the string that you're indicating. That's exactly what a C-style string does. A C-style string uses the null character to designate the end of the string. So just like previously we just had a scribble on this tape, if one of the characters of a character array is the null character, then that indicates that the string ends at this point. Now, the null character is not part of the string. It is used to flag the end of the string. All other characters in the character array are ignored regardless of their value. They may be other characters, entire phrases, but as far as we're concerned, once in a character array you reach the null character, that is the end of the string that that character array represents. If a character array does not have a null character, it is not a string, or perhaps it is a malformed string. That is, the programmer made a mistake. When calculating the length of a string, the null character is not counted, because the null character is used to flag the end of the string, so the count ends with the previous character. Now, this is interesting. Remember that the default value of a character is the null character. So when the character array phrase is initialized, the first 8 characters are initialized to the phrase good day, but the character at index 8, the 9th character in the character array, and all other characters are initialized to the default value of a character, which is the null character. So this declaration, with the initialization of the first 8 characters being good day, automatically represents phrase as a string of length 8. It's the capacity of the array that is still 100. Now, because the default character is the null character, here I create an array of capacity 100 called phrase, and I simply initialize each entry to be the null character. This phrase or character array therefore represents what is called the empty string, the string with no characters. Now, if you have a literal string, you cannot change that string. One of the nice features of using a local character array is that we can now manipulate the entries of that array, just like we can change the entries of an array of integers or floating point numbers. So here I have declared phrase to be a character array of capacity 100. The first 8 entries are the phrase good day, and all other characters are the null character. As there are more than 8 characters in the array, we're guaranteed that the character at index 8 is indeed the null character, and therefore this does represent a C-style string of length 8. So that is what the string will look like in memory. If we now pass this character array to be printed, the default assumption is that any character array, when printed, is assumed to be a string, so it will interpret the data as if it's a string, and it will start printing out the characters until it finds a null character. As soon as it finds a null character, it will stop printing to the screen. So this will print to the screen, good day, with an end-of-line character. Now, here I am making 6 changes to the given character array. So the character at index 1 is changed to an apostrophe. Again, you must remember that we must escape the apostrophe to represent the apostrophe as a character, and the rest of the characters, and note that we set the character at index 6 to be the null character. So here is our updated string. Notice that after the first null character, there is still the character y, but that doesn't matter because the string ends at the first null character no matter what. Consequently, if I print this string to the screen, then it will stop at the exclamation mark, printing out the phrase, good day. So there is our output if we compile and execute this program. Now, a few warnings. First of all, it's important for you to remember that the space is different from the null character. The space is a character that represents an actual physical space in the text. The null character is the ASCII character that has the numeric value equal to 0. So all the bits are 0. Also, if you use cout to print a character array that does not have a null character, the print mechanism will just keep on printing whatever is in memory until it finds a single byte that is all zeros. Again, this could be a potentially frustrating problem. Now, here's some homework for you. In this program, I have 2 character arrays, phrase 1 and phrase 2. I'm only going to print phrase 2 to the screen. However, if you were to compile and execute this program, the output would be hello there. So, go back to the previous lesson on the call stack and try to determine why this program prints both strings. Now here's one that's even more bizarre. Here I have an array of 3 integers, and then I have a character array that says hello with a comma at the end. I am now going to print the character array. If you print this, at least on a lot of computers, the output is going to be hello, I'm Bob. And if you don't know the reference, please do watch Blackadder. However, this is the output. Now you have to ask yourself, why does this print out the output, hello, I'm Bob? Now, some of you, depending on what type of processor you're using, may actually get a slightly different result. You might get the output, hello, I Bob. If you get this output, replace that integer array with this second integer array, and then you should get the output, hello, I'm Bob. Now, this is very subtle, and you're going to learn a lot about the workings of processors once you figure this out. But believe me, this is way beyond the scope of this course, so if you don't understand this and you can't figure out why it is doing what you think it is doing, that's okay. But this is there at least for fun. Now, let's try to author a function that calculates the length of a string. I'm going to encourage you to pause the video at this point to create a function that calculates the length of a string. So the first argument, the only argument, is a character array, and it's your job to count up until you find the null character and then return the length of that string. Recalling that if the first character in the string or the character array is a null character, then the length of the string is 0. So pause the tape now, and please do try this. All right, welcome back. Here's my solution. Now, in your solution, a lot of you may have had a separate local variable called length, which you then incremented. However, I'm going to use the loop variable to do double duty. Notice that the loop variable starts at the entry or at index 0. And notice that if the character at index 0 is the null character, what's the length of this string? 0. So I will return the loop variable. Now, if the first character is not the null character, then we'll increment k, and then we will check the character at index 1. If the character at index 1 is the null character, that means that the character at index 0 was the only character before the null character. Consequently, the length of the string is 1. And so once again, the loop variable k is storing the length of that array. You will notice that the second condition, or the condition of the for loop, is true. This loop will never stop until we find an entry of the character array that is the null character. So consequently, at the bottom, I include an assert false. So if this function ever gets to this statement, that assertion will fail because false can never be true. And so that's just protecting myself as the programmer. All right, hopefully you had some fun with that, and now we're going to go to the next problem. Now, we can compare if two strings are equal. So let's do so with a function. If you want, please pause the tape and try to author this function yourself. This function takes two arguments, both of which are character arrays, and there's the implicit assumption that each of those character arrays has at least one null character, meaning that both of those arguments represents a string. This function will then return either true or false based on whether or not the two strings are equal or different respectively. So please pause the tape and try this yourself. When you come back, I will present my solution. All right, welcome back. Here's my solution. As you can see, I have a for loop where the loop variable starts at 0 and is incremented with every single step or iteration of the loop. This loop variable will do double duty, being the index into the character arrays. The first thing I do is check, are the characters at index k different? If they are different, I immediately return false. I don't care what the differences are. All I care about is, at this location, do we have the characters different? And if so, then these two strings do not represent the same phrase. If, however, the character at index k is the null character, then I just return true. Now, why is that? Well, let's think about this. If the character at index k of the first string is a null character, then if the character at that index of the second string was not the null character, the previous condition would have been true, in which case the strings would have been different. However, at this point, we are guaranteed that both strings have the null character at index k. Consequently, all previous characters in both character arrays must also have been the same, and so consequently both strings must be equal, so therefore we return true. As before, we should never get to this point, and therefore we include an assert false statement. And of course, this requires us to include the C assert library. Now here's another question. What's wrong with this program? Here I have a character array, and I am setting the first three characters to be the word hi with an exclamation mark, and then the entry at index 3 is set to the null character. Consequently, this is the string hi. And when printed to the screen, usually this will successfully print the word hi with an exclamation mark. But what is the problem here? So take a look at the code and try to fix it yourself before you carry on. All right, welcome back. You probably noticed that the length of the character array is 3, which means that the entries of this array are the entries 0, 1, and 2. However, below I assigned to index 3 the null character. So if I wanted to store the string hi with an exclamation mark as a C-style string, then the capacity of the array needs to be at least 4. It could be larger, but it cannot be any shorter than 4, because the fourth entry, or the entry at index 3, needs to be the null character to flag the fact that the string ends at this point. Now, Go back to our previous discussion on the call stack and ask yourself what may have been overwritten by the call to assigning string 3 to the null character. Following this topic, you now understand the difference between a character array and a C-style string. Now, a C-style string uses a character array, but the assumption is one of the entries of the array is a null character, and the first null character represents the end of the string that is being stored. Consequently, the capacity of the array must always be at least one greater than the length of the string that is being stored. Now, unfortunately, there are very few languages in the world that can be represented using only ASCII. This includes English, Latin, and a few other languages such as the Zulu language, where in the 1800s Europeans introduced a representation of the language using European, specifically English, letters. If you want to represent any other language, you would of course need to use Unicode rather than ASCII. But this is beyond the scope of this course. Now, also in this topic, we looked at a number of functions that query information about C-style strings. What's the length of a string? Are two strings equal? And hopefully you had a chance to work that out yourself. Later in this course, once we see classes, then we will be able to investigate the C++ string class. But that's for a later topic. Here are the references, the colophon, and a disclaimer. Cheers!